Hi everybody, my name is Maxime Chevalier-Boisvert and I'm here to present to you my talk about Higgs, which is an experimental JIT compiler written in D. So my PhD research focuses on compilers and more specifically optimizing dynamic languages using techniques like type analysis. And Higgs is an experimental compiler that I'm writing for my research. The core of this compiler is written in D, which is the reason I'm presenting to you today. And so this talk is going to be about dynamic language optimization, Higgs, JIT compilation, and my research, and also about my experience implementing a JIT compiler in D. And I'll be concluding with some remarks about the use of JIT compilers for these compile time function evaluation. So dynamic languages are a family of programming languages that include JavaScript, PHP, MATLAB, Python, and others. And what these languages usually have in common is dynamic typing. So types are associated with values instead of variables. That is, variables can change type over time. And there's usually no type annotations in the language themselves. They also have the concept of late binding. That is, symbols are resolved dynamically instead of statically. So global variables are resolved dynamically. Function names are also resolved dynamically. They also often have dynamic loading of code, so functions like eval and load. And also the concept of the dynamic growth of objects, so objects as dictionaries, basically. So dynamic languages have a reputation for being slow, or at least significantly slower than static languages. This is probably because the easiest way to implement a dynamic language is using an interpreter, and also because naive implementations have a lot of overhead in them. Values are usually boxed, that is represented as a pair with a datum and a type tag. And in a language like Python, for example, CPython represents all numbers as objects, so pointers to objects. Basic operators, such as even the arithmetic operators, typically have dynamic dispatch hidden inside of them. So plus can be addition, but it can also be string concatenation, etc., depending on the types of the objects you're operating on. Global variables and field accesses are often implemented with hash table lookups. So if you want to make the code faster, if you want to optimize dynamic languages, a key aspect of this is to basically make the behavior more static. So remove the dynamic behavior, the dynamic dispatch, when you can prove that it's possible. And doing this requires access to type information. Now, you can get some of this type information through profiling, so observing the behavior of the program at execution time. But a better way to do it, I find, is using type analysis. So you want to be able to prove that a specific variable is going to have a given type at a certain point in a program. So for example, prove that some local variable will always be an integer, or prove that some function foo will never be redefined during the execution of the program, so that you can make the lookup of this function actually static instead of dynamic. So this is harder than it seems for a number of reasons. It's hard to optimize dynamic languages because many of them were not designed with performance in mind. If you complain about the performance of Python, the response you're typically going to get from the community is that you should rewrite the critical parts of your program in C because performance is just not a concern. There's also dynamic code loading, eval, makes optimization difficult because you don't have access to the whole program for analysis. And new code could break your optimization assumptions at any time. Dynamic languages also tend to have numerical towers, so infinite precision numbers. And so you need to have overflow checks in your program. And it's difficult to remove those overflow checks because it's difficult to prove that overflows will not happen. So Higgs is my attempt at exploring dynamic language optimization, and it has two main components, an interpreter and a JIT compiler. This time it's a moderately complex program. It's about 23,000 lines of D, 11,000 lines of JavaScript, and 2,000 lines of Python. It supports approximately JavaScript ES5 minus property attributes and the with statement. So the structure of Higgs goes like this. So it's kind of a typical compiler pipeline. So I start with the source code for the program. that I'm compiling source code for my runtime and standard library, and it goes through a lexer, gets converted into a sequence of tokens, which is then parsed into an abstract syntax tree. And then I convert this abstract syntax tree into an intermediate representation based on a control flow graph. And then this control flow graph can be executed immediately by the interpreter or eventually compiled by the JIT compiler. The interpreter can produce some profiling data, which is used by the JIT compiler to optimize the code. And the JIT compiler produces x86 machine code. I built Higgs in a succession of steps. So I started by building the lexer and the parser from scratch in D. I then started designing the intermediate representation and implementing the conversion of the AST into my intermediate representation. After that, I started to implement a very simple basic interpreter with integer arithmetic and function calls. And then I iteratively grew the interpreter and the runtime to cover increasingly more of JavaScript in succession. After I was confident that my interpreter ran most of JavaScript ES5, I started to implement an x86 backend, again from scratch in D. And on top of this backend, I started to build a simple JIT compiler to experiment with. And at the current stage, I'm implementing some of the basic research ideas I'm working on in the JIT compiler. And I'm also working with a collaborator to develop a foreign function interface and some basic library support for Higgs. And of course, at every step, I tried to add as many unit tests as possible to make sure that the whole thing was solid. So the interpreter in Higgs is used for three main purposes. It's used for profiling. It's also used as a fallback for features that aren't yet implemented inside of the JIT compiler. And it's also used to start executing code faster. So the problem with JIT compilation is that it takes time. And if a function is only going to be run one time or only a few times, then maybe it's not even worth actually JIT compiling. So the interpreter also serves as sort of like optimization level 0 in the system. It's designed to be simple, easy to maintain, quick to extend and experiment with, and also what I would call JIT-friendly. So the design of the interpreter is sort of deliberate to play along nicely with the JIT compiler. At this time, it's quite slow because performance wasn't really a concern for the interpreter. So it takes about 1,000 cycles per instruction. The structure of the Higgs interpreter goes something like this. So there's two stacks. There's a stack for words, and there's a stack for type tags. This is the advantage that I can access values on the stack in an unboxed representation immediately. Higgs also manages its own heap, which is based on a copying collector. So there's an allocation pointer and a heap limit pointer. And there's also an instruction pointer that points to the current instruction in a sequence. Yes?
So I assume that there's an invariant that the stacks are the same size, right, at all times?
Yeah, they have the same size.
And you know, could you give a bit more detail about the trade-offs of choosing two stacks instead of one that interleaves the types and the values?
Okay, well, the obvious disadvantages would be that you're using a little bit more memory. So I use 1 byte per type tag, so you're using 1/8 more memory. You're also using 1 more register, so I have 2 stack pointers. So those are the main disadvantages that I see. The advantages would be that you don't have to box and unbox your values. You don't have to do NaN tagging on floating point values. You don't have to do any shifting of pointers and integer values. So you have access immediately to an unboxed representation. I also think that this might actually work nicely for performance because modern CPUs have multiple execution units, and so possibly the type operations and the value operations can execute at the same time. And the goal in the end is that the JIT compiler should know most of the types, and it should not even have to touch the type tags at all, ultimately. So that would be the goal. So when I said JIT-friendly, I made a few design choices for the interpreter. One is that it's a register-based VM, and it's not stack-based as in bytecode, because this is easier to analyze and to optimize. The IR is based on a control flow graph and on an AST because it's closer to machine code and again easier to reason about. The interpreter stack is an array of values and words that's directly reused by the JIT compiler. And most importantly, the interpreter is not recursive. So the interpreter doesn't call itself when it does a function call. And this is necessary to be able to introspect the stack and be able to go in and out of the JIT compiler during interpretation. So the intermediate representation looks something like this. So if you had a function like Fibonacci, in gray, inside of the function, you would have multiple basic blocks. And inside the basic blocks, you have a sequence of instructions. The last instruction of each basic block is a branch instruction, and the instructions are all in tree address form. Higgs works with what I call low-level instructions, which simplifies the design of the interpreter, because the interpreter only deals with simple, basically machine-level operations. So the interpreter has instructions like integer multiplication, floating point multiplication, load, store, call, and return, but it actually knows very little about JavaScript semantics. It also simplifies the JIT because it means I have less duplication of functionality. Basically, I'm not re-implementing JavaScript semantics both in the interpreter and in the JIT compiler. This is also very good for the JIT because many of the operations in JavaScript have implicit dynamic dispatch. For example, the plus operator in JavaScript, like I said before, it can operate on integers, floating points, and strings. And it can also result in function calls if you're doing like a two-string operation on an object. And so you don't want to have to implement that in a JIT in terms of x86 assembly. So what I do instead is that I have some amount of self-hosting. So the runtime and the standard library are implemented in terms of an extended dialect of JavaScript that exposes low-level operations. So the primitives are compiled and inline and optimized like any other JavaScript code. This has the advantage that it's easy to extend and change the runtime. It has the disadvantage that the compile time is a little bit longer because I have to compile my runtime library also. And inlining is critical because if I can't inline my primitives, then the performance is going to be bad. So this is an example here. I have a function implementing the JavaScript less than operator. So the first thing I do is I check if x is a machine integer, then I check if y is also an integer. And if I know that both x and y are integers, I can use a machine less than instruction to do my less than operation. Otherwise, I'm going to have to check for floating point values and also strings and handle the more general cases. So Higgs manages its own heap for JavaScript objects using a copying semi-space stop-the-world garbage collector. This is the advantage that it's very simple and also that it's very fast to allocate. You can do it just by incrementing a pointer. It's got the disadvantage that references to D objects must be kept alive. So if I have a reference in my JavaScript heap to an AST or a function object, I have to keep it alive somehow so that D doesn't just collect my function. Also, when the interpreter manipulates references that are inside of my JS heap, the Higgs garbage collector might move those objects, so I have to be careful. Fortunately, the second problem isn't very hard to solve because since my instructions are very low level, most of them don't trigger garbage collections, and so they can't result in the objects moving around. So I only have a few instructions that I really need to worry about. So the picture looks something like this. So the interpreter might have references to objects inside the Higgs heap, and it might also have references to instructions, for example, inside of the D heap. If I have closures inside of the Higgs heap, they might refer to their implementation function. And so the interpreter has to have like a little table of references to functions that are still alive so that those functions don't get collected. And the Higgs garbage collector is going to remove functions from that table when they're unreachable, basically. So the JIT compiler in Higgs targets only x86-64 for simplicity, and it kicks in once functions have been found to be hot enough, so word compiling. This is done with execution counters on basic blocks. And right now, the JIT compiler is fairly basic. It doesn't do inlining, and most of the code is function calls, but it still results in the speedups of 5 to 20x. And I expect that soon with inlining and a few more tweaks, it'll be able to reach speedups of about 100x over the interpreter. So what I'm currently doing in terms of research is exploring this idea of context-driven basic block versioning. So it's an idea that's similar to procedure cloning, but that operates at a lower level. So basically, I'm specializing code, specializing basic blocks based on low-level type information and register allocation states, and also eventually probably based on accumulated information during compilation. I'm in the process of integrating this in the JIT. And it's interesting because it's got some similarities with trace compilation, but it works within a method-based compilation framework. So imagine, for example, that you're compiling a simple for loop. So you might have a basic block that implements the loop test. You might have another block that implements the loop body. Here we're doing some operation on 3 variables, x, y, and z. And then I have another basic block that does the loop incrementation. And when my loop test fails, I'm going to jump out of the loop to a loop exit block. So now if I'm compiling this inside of a JIT compiler, when I start compiling the loop, I might have a certain assignment of registers to variables to registers and also to stack slots. And the issue is going to be that pretty often once you're done compiling your loop and you want to jump back to the start of the loop, you're going to find that the assignment of registers doesn't actually match what you had to start with. And so the typical solution to this is to compile a little stub of move operations, basically to try to match the different register assignments. So this is not super efficient, but it's what most compilers will do. But what if instead you could compile a second version of your loop body and your loop test? So basically you compile a new version that works with the new register assignments, and you don't bother doing move operations. So the idea here is that we would create versions of the loop until we reach a fixed point where the register assignment at the end is going to match the register assignment at the beginning. So the advantage would be that we're automatically doing a little bit of loop peeling and tail duplication when useful. We're having fewer move operations, and we can make simpler register allocators more efficient. This is also a little bit similar to trace compilation because we can use this system to accumulate knowledge during compilation. And also we can use it to specialize codes not just based on register allocation, but also based on type information. Possibly even do constant folding during compilation. So one way to see this is that traditional compilation and control flow analysis compute a fixed point, basically. So at each basic block, I want to have solutions that agree for all incoming control flow edges. So I want to have an answer that is pessimistic and that agrees with all the possible inputs. If we do block versioning instead, we allow for multiple possible solutions to be true for a block at the same time. And we don't necessarily have to sacrifice and pick a pessimistic solution. So we're basically shifting the fixed point from the analysis to the creation of new blocks. We're doing a fixed point on the versioning of blocks instead. So obviously there's a number of research questions. If we do this, we're going to get a certain amount of code blow up. So are we going to have to put a cap, a limit on the number of versions of basic blocks? What can we do to avoid too much code blow up? What kind of performance gains can we expect? What kind of information should we use for versioning? Should we go as far as using this for constant propagation? Or what kind of granularity of type information should we use? And how much information is too much? Because presumably, the more information we have, the more context sensitive we are, the more code blow-up there's going to be. And of course, there's a question as to the effect on compilation time, because the more versions you create, the more time you're going to spend compiling all that code. Okay, so now moving on to the second part of my talk. Yes?
Before we move on, if you had infinite resources, the proverbial, how would you integrate Higgs' own GC with this heap?
I had infinite resources.
Yeah, if you said, you know, GC is going to be my focus here, I'm going to design the perfect system, how would you design it?
Well, I don't really have an answer to that, honestly, but my area of research isn't really garbage collectors. I think that garbage collectors are sort of an ongoing research problem, but you know, what is the perfect garbage collector? What is the garbage collector that's going to work with multiple threads, that's going to allocate very fast, that's going to not suffer from problems when integrating with like a foreign function interface? And I don't really know. I guess.
So probably simplicity was sort of a good goal for your design, right? So
yeah. I picked a stop and copy collector because it was simple and because it simplified my work, and I felt more confident implementing something simple like that.
Okay, and sort of a question from our camp would be to you: what did we do right and wrong in the design of this own garbage collector? Did it work well for you?
It seems to have worked pretty well for me so far. I would say that it behaved predictably, like as I would have expected it to behave. But I haven't maybe stressed it enough to really be able to say how much it scales at this point, I would say. Okay. So, well, why did I choose D? Well, JIT compilers need access to low-level operations. They're systems programs, so they need to do memory management. They need to be able to allocate executable chunks of memory. They need to do raw memory access. They need to use systems libraries. They're also very complex pieces of software. You have a pipeline of code transformations. You have several interacting components. If something breaks in one of your code transformations, chances are you're going to notice. I wanted to have a language that would help me mitigate all this complexity that was expressive enough. I also wanted to have garbage collection because managing memory manually during all of those AST and IR transformations is very error-prone. I came from a C++ background, and I had a lot of experience with it. C++ is a very powerful language, but it's also very verbose. There's a lot of repeating of type declarations everywhere. I came to find working with C++ rather frustrating over time because of all the redundant declarations. Header files force like a poor organization of code. They have annoying constraints on what you can put in a header, what you can't put in a header, like templates, for example. C has macros, but they're kind of messy. The C++ templates feel sort of limited, and there's no standard GC implementation. At the same time I was looking at D, I also looked at other options like Go and Rust. Rust was very young when I started my project. It was changing a lot. It was still in flux. I've been told that it's still changing quite a bit, so it really wasn't a realistic option for me. Go was interesting, but it didn't have templates or generics. I was told that it couldn't do pointer arithmetic without first casting your pointers to integers and then doing your arithmetic and casting them back. It felt very minimalistic and very opinionated, you know, basically like if you're not coding in the Go style, you're doing it wrong. And I didn't really feel comfortable with that. But then I found out about D. D has garbage collection by default, but you can still do memory management. It's been around for over a decade, so presumably it's got a fair level of maturity. It's got an attractive collection of features like mixins, compile time function evaluations, templates, closures. And it gives you the freedom to choose among all those features what you think is best for your software. It's also got a very active and responsive community. So those are all the reasons why I chose it. I found, coming from a C++ background, learning D felt fairly intuitive. The languages are similar enough. D is actually slightly less verbose. And most of the adaptation was just learning new idioms, new way of doing things. Like sometimes D has a more concise, better way of doing certain things that I didn't know about. But I started programming my Lexer basically within 1 day of downloading DMD. D has a lot of small features that I would say make the language pretty pleasant to use. Like a lot of them aren't really revolutionary, but more common sense. But here are some of the features that I found in D that made me very happy. So the for each loop, it's very simple, but it allows you to iterate over some collection or iterate over a hash table or an array with both the key and the value at the same time. You don't have to declare the types. And it's common sense, but it makes you wonder why other languages like JavaScript, for example, don't have something equivalent to this. It's very nicely designed. In and not in, having a lot of experience with JavaScript, JavaScript has an in operator, but it doesn't have the negation of it. And when I saw this in D, you know, it's like, why didn't they think of this? Type inference is not exclusive to D anymore, but when I coded in C++, there was no auto keyword. This is very useful. It saves a lot of code duplication. It makes refactoring a lot easier. Delegates, of course. This is part of a unit test in my backend, testing the encoding of machine code instructions. So I'm having a delegate that generates machine instructions, and I'm checking that the encoding is what I would expect. Type ranges, again, a very simple feature, but when you're writing systems code, it's very useful to just have a min and max to know what's the range of a given type. The D garbage collector, I had to make it interact with my garbage collector, which means that I did memory management manually. I also had regions that were not collected by D. I had to maintain references to the D heap alive. This turned out to work better than expected. I found, like I said, that the D garbage collector behaved fairly predictably. I expected to get a lot of garbage collector bugs, but this actually didn't happen. Another pleasant thing that I found was that I could mix templates and mixins together. So here, this is a part of my interpreter where basically I templated the implementation of integer opcodes of my interpreter. So I have a mixin string in green that basically just has the operation that has to happen on those integers, and all of the boilerplate code of those instructions is inside of the template. The build system was very pleasant to use. It's a lot simpler to write a make file for D code than it is for C++ code, so this reduces the need for complex build tools. And of course, the community, the centralized dlang.org website is a great resource. The forums, the documentations, and the downloads all in one place. I find that most languages don't really have a go-to place like that. Now, unfortunately, I told you about a lot of the things that I liked about D, but if I said that everything went perfectly as I implemented my compiler, I'd be lying to you. One of the reasons that I chose D was CTFE, and in particular, Mixins. You know, I saw Mixins as a way to create a powerful macro system that could allow me to create little domain-specific languages. And this is arguably one of D's most powerful features. But unfortunately, I did run into some problems. So what I wanted to do was I wanted to control the memory layout of objects inside of my JavaScript heap precisely, and I wanted to be able to access those objects from both D and JavaScript. So I wanted to make a little declarative language that would describe the layout of my objects, and then I would automatically, at compile time, generate D and JavaScript code that would implement my getters, my setters, functions to allocate objects, functions to traverse objects inside of the garbage collector, all automatically generated. So the language looked something like this. So here I have the layout of a string object. It has 3 fields, has 1 field for the length, 1 field for a hash code. It has a data field, which is UTF-16 characters. Then I had other objects in there, like a string table for hash consing, JavaScript objects, JavaScript arrays, and so on and so on. But unfortunately, it broke down. As my code became more complex, generating a few thousand lines of code became very slow. And then I ran into a memory leak that used up all available memory in my system. And my computer ended up locking up during compilation, completely deadlocked. And I didn't know what was happening at first. I thought there was a bug in my code. But then I figured it out. And so I went to the D forums to ask for some help. I was told that it was a known compiler bug, but it would be fixed within a couple of months. And at that time, I was kind of frustrated and confused. I didn't really know what to do because I needed this to work immediately. So what I ended up doing is I ported my little domain-specific language to Python, unfortunately. Yeah. So you might think that it's because I had some crazy complicated code that really like exerted CTFE a lot, but this very simple, very short program will produce the crash I was talking about. I also ran into some issues with templates. I wanted to have templates with lists of integer arguments to describe my instructions, but I ran into a known compiler bug, and so I resorted to having more code duplication. But I expect that this will be fixed eventually. Another problem that I ran into, I don't think I can really blame DMD for this, but it was kind of unexpected. I found that I had issues with assertions. So if I trip an assert in a function that's indirectly called by machine code I generated myself, it will throw an exception, and it will try to unwind the stack. But when it gets to the stack frame that is my own JIT code, it doesn't know what to do, and so it segfaults. And so probably assert should print an error message before it tries to unwind the stack. But I guess that's a design issue. Yes?
Oh, I know what the problem with that is. The stack unwinder expects a BP as the frame pointer, and that the BP points to the previous frame pointer. And that's what it walks. And if that is not set up like that, it will crash walking the stack.
Yeah, that was my guess.
So I would say you may want to submit a bug report, and either we need to document this requirement or fix, change the design of assert to. Yeah,
honestly, I didn't really know what to do with this issue because it's kind of a, I don't think that the design of my compiler should necessarily guide the design of DMD because I'm one person with a very, very specific narrow use case. I actually thought maybe I should implement my own assert function that does what I want. Yes.
You can implement your own assert function because what assert does is it calls through a pointer to a function. And you can override that with your own function and do whatever you want. It doesn't have to walk the stack at all. So yes, you can make this work.
Yes, that's probably what I'll end up doing. Another issue that I had was with unit test blocks. I used a lot of them to test my compiler, but I kind of wish that I could name my unit tests. I kind of wish that unit testing reported failing tests at the end. Also had a minor issue because Higgs, when you start it with no arguments, it will go into a read eval print loop. But this is not really the behavior I want. If I start Higgs with unit tests, I don't want it to go into a read eval print loop. So I had to use some little tricks to get it basically not to do its default behavior when doing unit testing. I also kind of wish there was a way to select which tests are going to be run more precisely. I was kind of tempted to write my own unit test framework, but I decided against it because I didn't really have the time. This last one here is kind of a pet peeve, but I've been using associative arrays to map objects to behaviors. For example, here, this is in my backend. I wanted to map different opcodes to functions that generate code inside of my JIT. But I have to initialize those associative arrays inside of a static constructor. But then I ran into issues with cyclic module dependencies in static constructors. So I kind of wish that there was a way to initialize associative arrays outside of those static constructors, maybe constant associative arrays. Okay, so JIT compilations for these CTFE. So as I mentioned earlier, JIT compilation has a cost. And so what mainstream VMs typically have is they have a JIT with multiple optimization levels. Or in the case of Firefox and Higgs, an interpreter and a separate JIT compiler. So because JIT compilation takes time, it sort of has to pay for itself. It's only worth it for functions that run for a long time, not worth it for functions that only run a few times or even not at all. Because the majority of code doesn't need to be optimized. So does CTFE actually need a JIT compiler? I think this is a legitimate question. It depends on what people are doing with it. So I think for the typical scenario of source code generation inside of Mixins, where you only do like string concatenation operation, you probably don't really need fast CTFE for this. But at the same time, maybe we have to be more open-minded because if CTFE is faster, it will open doors. If CTFE is capable of more things, then people will probably use it for more. For example, generating procedural content at compilation time. So my advice would be it's probably not worth it to optimize a CTFE interpreter to that. For example, I spoke to the Mozilla JIT engineers, and they tell me they have a bytecode interpreter right now, but they're planning to switch to something simpler and slower. They're planning to actually go back to an AST interpreter just because it's easier to maintain and to work with. And they really think that interpreter speed doesn't matter when you have a JIT. I would say if you're starting to implement a JIT compiler, you should probably go with something simple. For example, maybe something stack-based, something that doesn't do register allocation. It will compile very fast, and it will be much faster than any interpreter, no matter how much time you spend engineering that interpreter. So it'll pay for itself very quickly. If you have code that's really hot inside of CTFE, maybe you could actually reuse some of the DMD infrastructure to compile it. And maybe you could even cache some of that code between runs to save time. So you could have an architecture that's tree level, something like this maybe, where the first level is an interpreter. So if you call a function once inside of CTFE, it just goes through the interpreter. If you call a function enough times, it can get compiled by a baseline, simple, non-optimizing JIT compiler. And then if you really call it a lot, maybe you can actually hook into DMD somehow, either reusing the AST that you had before for the interpreter or starting directly from source code, whatever is more practical to integrate, and then actually generate optimized code. There's some other considerations, such as, can you precompile some of the library code that's going to be used in CTFE, because the interpreter could call into compiled code. Presumably, most string and array operations could be precompiled. It's a bit trickier with templates, but maybe you could cache some compiled templates based on the arguments and then save time. Reoptimizing functions in the middle of a call. So if you have a function that executes a loop that runs for a long time, it's actually complicated to replace your implementation of that function, but I think that's probably not a concern for CTFE. So I'm going to conclude with a few suggestions. One of them I already mentioned. I kind of wish that associative arrays could be initialized outside of static constructors. Maybe this could be limited to constant static arrays. I don't know how practical it is to actually implement this, but it would be really nice if that feature was actually in D. I think it sort of goes with making the language easier to use, sort of like with the inference of immutability, for example. Like the compiler has to do more work, but it makes it more practical for programmers. Integer types. So D seems to guarantee the size of integers, but names like short and int and long don't really tell you much about the type itself. And so as someone who is always including stdint, in the code because I want to know what I'm using, I kind of wish that names like int8, int32, and so on were in the default namespace, and maybe that people were even encouraged to use those types, because then maybe programmers would be more aware of the limitations of the types that they're using. In terms of documentation, I would say I still don't know D that well. I still feel like I could be exposed to more idiomatic D code. I wish that there was some sort of repository of idiomatic snippets of D code that are like the good way of doing things, so that I could learn the language faster. In conclusion, I would say I had an overall positive experience using D. I did run into some problems, but no showstoppers. People often accuse C++ of being too complex, of having too much. I feel like D has pretty much all the features of C++ and maybe even more, but it sort of feels like more of a cohesive whole. Like it's been engineered with more hindsight, and it fits together better, even though it has all these features. I don't have any quantitative numbers. I didn't try implementing all of Higgs in C++, but I can also say that it definitely felt more productive in D. So if you're interested in checking out Higgs, it's available on GitHub. I would appreciate your comments and also potentially pull requests if you're interested in contributing.
Questions?
Yeah, I just want to make a comment, not a question. Just that the reason that CTFE is so slow is not because it's not using a JIT. It's got more basic problems than that. I'm getting very close to addressing those fundamental issues, but I've been working on this for 1.5 years. Almost done, but yeah. So it's, yeah, just a lower level problem than that. Or higher level.
So I guess it's somewhat of an obvious comment, but you said you used Python for your DSL. Couldn't you just have like offline generated your DCTFE code just the same, like reused your CTFE code but just offline compiled your code? Like offline generated your code?
That's actually a good point. Well, I guess I didn't mention, I sort of had other frustrations with the CTFE, which is that at the time I couldn't use format, for example, so the code was kind of clumsy.
Okay.
And I could have just used it offline, like you said. I kind of felt like, well, Python is a nice language for working with strings, so if I'm going to convert, maybe I might as well.
For the JIT, you say you blocks and you keep iterating on them until you hit a fixed point. Is that within one loop, or if you iterate and you iterate and you iterate and you find yourself, hey, wait a minute, I could go back to something that I did previously, and you basically like unroll the loop 3 times or something like that?
Well, it doesn't really iterate over the blocks in a loop. It's more like when I hit a point where I need to jump to a block, I'm going to have a context, so like some type information, register allocation state, and I'm going to request a block that matches this context. And so if it doesn't exist, it's going to get generated at that point.
Okay.
When you generated the code for a block, you said if the register usage at the end came out different from the beginning, you generated a new block again. Well, what happens if it sort of flip-flops between 2 states? Do you keep generating new blocks, or do you detect that?
Well, if there's already a block with a register assignment that's been compiled already, like it wouldn't just generate a new one.
Okay.
Yeah.
So at the end of the first half of your talk, you talked about some of the research questions like code blow up, exponentially increased code duplication. Do you have any early results on that?
So far, it doesn't really seem to be a problem, but I don't do inlining in my system. So I expect that the bigger a function gets, the more blocks it has, the more of a problem it's going to be. So far, the biggest functions that I have, I get like a code blow up of like 20% only, which is really small. Yeah.
In the same vein, it sounds like you're looking at some sort of a cache eviction strategy or a sort of garbage collection for these generated blocks. Did you approach things that way?
I didn't actually approach things that way, but there's sort of, like we already have plans for like a phase 2 system, maybe where the blocks don't actually just get generated when compiling a function, but they would actually get compiled lazily. So sort of like an incremental function compiler where only the parts of a function that have been executed will get compiled. And then when you jump to a block for the first time, it would get compiled. A new version would get compiled, and maybe even some sort of incremental inlining of functions, but that's not quite there yet.
All right. Well, let's give a hand to Maxime. Thanks very much. 6 minutes break.